Hello everyone, a very good afternoon. Just confirm me whether my voice is audible or not. Am I audible? Keep commenting in the chat box given and I'll make sure that you'll revise the half of strength of material today. Keep commenting whether my voice is audible or not. Am I audible to you? Am I audible to you? Just give me a hi if I am audible to you. Okay. So I welcome you all to the Gate Booster series of IMS Gate Academy. Myself Prateek Mishra, and today we will be seeing half of the subject of strength of material, which is one of the very important subject for mechanical and civil engineering students, my dear. If I talk about mechanical engineering students, strength of material has a weightage of around 7 to 9 marks in the examination. For civil engineering students, again it's a very important subject because it serves as the basis for structural analysis, reinforced cement concrete and steel structures. So one subject governing the three subjects, that is how important strength of material is for civil engineering students. So today I'll make sure that you learn all the basics. Second, you enjoy whatever questions we will discuss. And through the questions, we'll try to learn the entire subject of strength of material in these two sessions. Today we will going to discuss the first part of strength of material, and tomorrow same time we will going to discuss the other half of the strength of material. Okay, so before starting this session, I have to make few announcements. First one is, my dear students, join our Telegram group to get the schedules of our YouTube lectures, to get the PDF of whatever sessions we are conducting right now, to get the details of vacancies that are upcoming for engineering graduates, to get the daily quizzes. You can join our Telegram group. Link is here itself and it is also there in the description box. We ensure that in our Telegram group that we paste daily quizzes so that student gets in regular contact. Hello JP sir. A very good afternoon. Hello Sandeep sir. Thank you so much. So this is the first announcement, my dear students. The second one is, we at IMS Gate Academy offer you different types of courses, and we will be targeting Gate 24 and Gate 25 in our classroom courses. If I talk about our classroom courses, we conduct them in 3-4 different manner. First one is the offline classroom program. Second one is the purely online classroom program. Third one is the hybrid program where you enjoy the fusion of offline and online classes. And last one is a self-learning program. In all these programs, we provide you with 800 hours of live classes with interaction. You have live doubt solving here in these sessions. We provide you with theory and exercise book, and we provide you with good question bank which contains 30 plus years of previous year GATE questions. My dear students, in the GATE preparation journey, this GATE question bank is the game changer. Because all the concepts that are asked in GATE examination are somewhere repeated over down the line. Though questions may not be repeated, but the concepts will surely be repeated. Next one is, you will get 12 personalized one-to-one mentoring sessions, my dear students. And I proudly say this, IMS Gate Academy is the only institute in the country to provide one-to-one mentoring for all the engineering graduates. GATE is an hectic journey of 8 months which requires continuous dedicated efforts with consistency, and along with that, you require continuous motivation. If you have a proper plan for 8 months, how you will going to proceed with the GATE preparation, then your motivation keeps updated, right? Your motivation is still there with you. So these mentoring sessions help you to stay motivated in this long hectic journey of GATE preparation for 8 months to 1 year. Last, we provide you with 130 plus online test which gives you a real feel of GATE examination. 130 plus test contains chapter test, subject test, multiple subject test, advanced subject test. Then we provide you with a full length mock test along with your all India rank. So whenever we release our full length mock test, if you attempt that test on the same day, you will get the All India rank for yourself. That will help you to actually analyze what is the state of your preparation, where you are actually lagging and which all concepts require continuous improvement. So that is what we offer at IMS Gate Academy. So these are some of the few announcements that I have to make. Now let's start with the very interesting subject of strength of material, my dear students. We start with, this will be our session flow. We will start with simple stresses and strains. Then we will discuss thermal stresses. Then we will discuss shear force and bending moment diagram, how to draw that and how different questions can be framed from it. Then we will discuss the bending stresses, and last we will close our session by discussing the shear stresses. When you look into the session flow, you will realize that this is half of the strength of material, and I'll make sure to complete half of the subject in just a span of 3 hours. The only thing required from your end is stay tuned with the session. Do not miss even a single moment, and that will be my guarantee to cover each and every aspect of these 5-6 topics that are listed here. Okay, so let's start with a very simple thing, my dear students. First of all, when we start the analysis of strength of material, my dear students, most of the student has the confusion that whenever we are discussing something, we take few assumptions, right? So I start with those assumptions. So first topic of discussion is assumptions in strength of material. So what is the first assumption? First assumption is material is homogeneous. Second, material is isotropic. And third one is material is elastic. Okay, so these are the primary assumptions that we use in entire analysis of strength of material. First of all, what do you mean by material is homogeneous? Material is homogeneous means that the property of the material is same along any one particular direction. If we move along any one particular direction, then material property does not change. For example, if this is my body and I'm moving in any one particular direction, okay, if this is my body and if I'm moving in any one particular direction, say this direction, then the material property will remain constant in this direction. Say if the material property is Young's modulus, then the Young's modulus Ex will be same as I'm moving in one direction. If I move in this direction, if I move in the other direction, like if I move in this y direction, then again the material property is same at all the points, Ey, okay. But homogeneous material does not mean that Ex is equal to Ey. This is not there. Homogeneous material only means that the material property is same along any one particular direction. If you are moving along one particular direction, material property will be same. Then comes your material is isotropic. Material is isotropic means that if you are at a point, then the property of the material is same along all the directions. Now when you relate this homogeneous and isotropic, combinedly it means that property of the material is same at all the points in all the directions. So these two are used in combination. I hope you understood this. Next one is material is elastic. This means that when you apply the load over the material and after releasing the load, the material will regain its original shape and size. Here I would like to mention one simple difference between mechanics and strength of material or mechanics of material is, in mechanics what we do is, we analyze the material when the material is under the state of motion. But when we talk about the strength of material, we will be talking about the body under static equilibrium. Means the material is not under motion, but due to the external load, this material will going to deform. And how this deformation will happen, that is the total analysis in the subject of strength of material. So most important part, or I will mention this as a note point, in strength of material, body is under the state of static equilibrium. Body is under the state of static equilibrium, right? Now, what does this static equilibrium means? Static equilibrium means that you can apply all the equilibrium equations. The material is not moving, all the forces are balanced, and when we talk about the balanced forces, I can clearly say that you can apply the static equilibrium equations over that material. When the material is said to be under the state of static equilibrium, we say that the summation of horizontal forces equal to 0, summation of vertical forces equal to 0, and summation of moment about any point equal to 0. So these are my primary equilibrium equations that I use to analyze any body. Okay, you have seen that we consider a body like this, and over this body we apply forces in the either direction. We apply load like this. This is load P. And again we apply equal and opposite load like this. The reason of applying this load is that we want the body to be under the state of static equilibrium. We do not want this body to move along any one particular direction. Equal and opposite forces, when you apply over the body, then the net force over the body becomes 0. And when the net force over the body becomes 0, the body is said to be under the state of static equilibrium. Okay. Now, the thing is, when you have applied this load over this body will undergo some deformation. This body will undergo some deformation. They say this is the deformation delta. Now our entire analysis of strength of material is related how much this deformation will come, okay, and what are the resisting force which are resisting this deformation due to the external load, okay. So from here I'll continue with my discussion with a very simple topic of stress. Can you tell me what do you understand by stress? Can you tell me what do you understand by the term stress? What is stress? Can anybody tell me in the chat box, what do you understand by stress? Okay, so when you look over this body, I said that this body is under the state of static equilibrium. When I say this statement, it automatically means that even the portion of this body will be under the state of static equilibrium. Okay, so if I consider a section XX like this, right, due to this external load, this deformation will come, and in order to resist this deformation, internal resisting force will be developed inside the body. This internal resisting force per unit area is termed as the stress. Okay, so R is the internal resisting force. R is the internal resisting force. So if I draw only this portion of the body, it looks like this. This is my load P. And in order to resist the deformation, the internal resisting force will be developed like this. Okay, this R is the internal resisting force and this is my external load P. So if this body is under the state of static equilibrium, even the portion of that body should be under the state of static equilibrium. And when this portion is under the state of static equilibrium, I can say that the summation of horizontal forces equal to 0. And from here I can write P is equal to R. This is what we mean by if the body is under the state of static equilibrium. P is equal to R. And from here only, I'll define stress. So stress is internal resisting force per unit area. Okay, so this is my stress. Internal resisting force per unit area is my stress. Now, my dear students, based on which area we take, this stress is of two types. So next is the types of stresses. First one is known as your engineering stress. And second one is known as your true stress or actual stress. Observe this very, very carefully. True stress or actual stress, right? So this was the initial position of my body. This was my body initially. When I have applied load over this body has undergone the deformation and this body got deformed like this. This is the deformed shape of the body, right? This is the deformed shape of the body. And this deformation has occurred due to external load P. As you can clearly observe that, initially the length of the body was L. Now the length has changed to L dash. Initially the area of cross section was A naught. Now this area has changed to A actual or instantaneous area, right? So which area to take? If you are taking the original area to calculate the stress, that is known as your engineering stress. So engineering stress sigma naught is equal to internal resisting force per unit original area A naught. So sigma naught is equal to R divided by A naught, right? Whereas your true stress is equal to the internal resisting force per unit the actual area. So actual stress sigma actual is equal to internal resisting force per unit actual area, A actual. So these are your types of stresses based on which area you are considering, whether you are considering the original area or whether you are considering the actual area. These are the types of stresses. Okay. Now next, what do you understand by strain? So basically, as you can clearly see from this diagram, due to this external load, this increase in length has happened. This is the change in length has happened, right? So strain is defined as change in length per unit original length. Strain epsilon is equal to change in length per unit original length or per unit length. Change in length per unit length. Okay. I will write this as delta L by length. Again, which length you are taking? If you are taking the original length L, then it is known as your engineering strain. If you are taking this instantaneous length L dash, then it will be your true strain. So based on the type of length you are taking, this strain is again divided into two categories. So I will write here types of strains. So first one is your engineering strain. And second one is your true or actual strain. So which length you are taking, based on that, you can define two types of strain. If I talk about engineering strain, so epsilon naught is equal to change in length per unit original length L, right? Whereas your true strain, epsilon actual, is equal to change in length per unit instantaneous length L. So based on the type of length you are taking, you have divided two types of strains, engineering strain and your true strain, right? Now, this can be written as your epsilon A can be written as dl by L, instantaneous length, and this we integrate from L to L dash, right? So your epsilon actual comes out to be natural log of L dash to L. So this can also be the expression to calculate your actual strain. Epsilon actual is equal to natural log of L dash by L, where L dash is the instantaneous length and L is the original length of the member. Similarly, we can have a relation between engineering stress and your true stress. So that relation is your actual stress or true stress is equal to your engineering stress. This is epsilon actual is equal to epsilon naught into 1 plus minus epsilon naught. So this is a relation between actual stress and your engineering stress. All the relations that I am writing over the board are very, very important relations because we have seen that frequently questions are framed from this area. Okay. So this is the thing. We have talked about strains. We have talked about stresses. Now next one is your Hooke's law. Next one is your Hooke's law. What Hooke's law says that? Hooke's law says that stress is directly proportional to strain. Before that, there are 3-4 assumptions for Hooke's law. First one is the material is homogeneous, material is isotropic, and the material is elastic. That we have already seen while from starting of this subject. So from Hooke's law, we can say that your stress is directly proportional to strain. When you remove this proportionality sign, you have stress is equal to Young's modulus into strain. So this is the relation that you already know. Stress is equal to Young's modulus into strain, right? Sigma is equals to E into epsilon. Now, my dear students, next I want you to calculate this. If you have a body like this over which a load P is acting, okay, then due to this external load P, length of the member is L. What will be the elongation of this bar? So elongation of this bar is equal to elongation of bar, that is delta L. So this elongation can be calculated using strain. Strain is equal to change in length per unit original length. Okay, just observe this. So I know that sigma is equal to E into strain, right? Sigma is equal to P divided by cross-sectional area, external load, since internal resisting force is equals to external load, therefore I can write stress is equals to P by area is equal to E into delta L by L. From here the value of delta L will come out to be PL by AE. This is your elongation of the bar. We have applied the load. This is the tension force, right? Therefore, we will get the elongation of the bar. On the other hand, if you have applied the compressive force, then the same thing will be the contraction of the bar. Very good evening. Very good afternoon, Rohan. Okay. So delta L is equal to PL by AE. This is your elongation of the bar. Now here one thing I would like to tell you. This AE is known as your axial rigidity. This AE will tell you the axial rigidity. And what is the axial rigidity? Axial rigidity tells us about the strength of material against the axial deformation. Means if the axial rigidity of the material is more, then more amount of load will be required to cause the deformation in the body. You can take an example of steel, and on the other hand, you can take an example of wood, right? First, I'm taking as steel, and second, I'll take aluminium instead of wood, okay? Steel and aluminium. We know that steel is more strong than aluminium. So, in order to cause 1 mm of deformation, the amount of load required in steel will be more. This can be understood like that axial rigidity of steel is more with compared to aluminium. That's why the amount of load required to cause 1 mm deformation in steel will be more. So I can say that axial rigidity AE for steel is more than axial rigidity of aluminium. That's why the amount of load required in steel to cause 1 mm deformation will be more. So my dear students, if you get any interview question or a question in the examination in which you are asked that which material will require more load to undergo 1 mm of deformation, you have to observe this parameter of axial rigidity. If axial rigidity is more, then that material will going to require more amount of load to undergo 1 mm of deformation. So for this axial rigidity tells us about the strength of material or the resistance offered by the material, resistance offered by the material against axial deformation. More the axial rigidity, more will be the resistance offered. Sir, stiffness is also like rigid. Okay, Devesh. So the thing is, axial rigidity is for the entire length. If the same resistance you consider per unit length, then that is known as your axial stiffness. Actually, I was about to come to that point. So first I would like to tell you axial rigidity. This is for the total length. So for the resistance offered for the total length against axial deformation is axial rigidity. On the other hand, you have one more parameter which is known as axial stiffness. So axial stiffness is the resistance offered by the material against axial deformation per unit length. So axial stiffness is defined as AE by L. What does this tells us? I think Devesh, I have answered your question. So axial stiffness is the resistance offered per unit length against axial deformation. So this is the resistance offered per unit length against axial deformation. So just quickly tell me, if I ask you, just quickly tell me if I ask you, you have to compare between two materials. Say, I give you one material copper and second material say iron, okay? And if I tell you that E of copper is less than E of iron, area of copper is same as area of iron. Tell me which material will require more force to undergo 1 mm deformation. 1 mm deformation, which material will require more force? Please tell me which material will require more force or more load to undergo 1 mm deformation. This is the data given to you. Copper, iron, and I am asking you which material will require more load to undergo 1 mm deformation. Iron will require more force. Very good, very good. Iron will require more force. Very good, Rohan. Very good, Devesh. Okay. Now by these words, how you have identified this? Since Young's modulus of copper is less, axial rigidity of copper will be less as compared to iron. Therefore, in order to undergo 1 mm deformation, iron will require more load. With this, please attend this very first question. I'll give you 1 minute of time. Please attend this. Just 1 minute of time. Attend this and tell me the answer. Keep commenting your answer in the comment box. Come on, everyone, quickly. C will elongate more. Okay, let's see. So question says that two circular rods of same diameter, please observe that, same diameter and same length. Same diameter and same length. Same diameter means their area of cross section will be same. Cast iron will elongate more as modulus of rigidity is less for this. Okay, let's see, Devesh. Two circular rods of the same diameter and same length are subjected to same magnitude of axial tensile force. Okay. One of the rods is made up of mild steel having modulus of elasticity as 206 gigapascal. The other rod is made up of cast iron having the modulus of elasticity of 100 gigapascal. Okay. So Young's modulus for steel is more than the Young's modulus of iron. Both the materials are homogeneous and isotropic, and the axial forces causes the same amount of uniform stress in them. If the stresses developed are within the proportionality limit of respective materials, then which of the following statement is incorrect? So if I just write down these two conditions, Young's modulus for steel is more than Young's modulus of iron, Fe. Second, area of steel is equal to area of iron. So from here, what we can say about the axial rigidity? Axial rigidity of steel, AE of steel, is more than AE of iron. If the stresses are same, stress in steel is equal to stress in iron. If stress in steel is equal to stress in iron, then iron will undergo more deformation because iron is weak against the resistance offered along axial deformation. So cast iron will going to elongate more. So for this question, your option number C is your correct option. I hope all of you have answered this correctly, right? Very good. Devesh has even explained that why iron will undergo more elongation. Okay. So this is one of the basic question, a 1 mark question that can be framed in your GATE examination. Let's continue with this. Moving on with this, let's discuss a very, very important parameter, and that is termed as your Poisson's ratio. So what do you understand by Poisson's ratio? Can you comment? What do you understand by Poisson's ratio? Can you comment in the chat box? What do you understand by the Poisson's ratio? Usually you understand Poisson's ratio by n number of definitions that are listed in the book. I made you visualize what do we actually mean by Poisson's ratio. Observe this. For example, again I'll take the same body which is under the action of load. This is the body which is under the action of load, right? This is the body. This is the body which is under the action of this external load. This is load P. This is also load P. If I just continue this diagram like this, this is the body I have, right? And this body is under the external load P. When you apply load P, this body, the length of the body will going to elongate like this. If length is L, it will going to elongate to L dash. Let me draw that also. It will going to elongate like this, right? It will going to elongate like this. Now observe the cross section. This is the cross section. This is the cross sectional area. Earlier, the width of the cross section was B. Now it is B dash. The width has been reduced. Earlier, the depth of the cross section was D. Now it is D dash. Depth is also reduced, right? So you have applied the load along the length, but the other two dimensions has changed. The width B has changed to B dash. It is reduced. The depth D has changed to D dash. Again, it is reduced. So this reduction in the lateral dimension due to the load applied along one particular direction is termed as the effect of Poisson's ratio, right? Or it can be termed as the Poisson's effect. Sir, upon tensile force along force direction, longitudinal, there is positive strain, and in the transfer direction, there will be negative strain. Very good, Divesh. Very good. Very good. So, longitudinal versus lateral. So, sir, with a very awkward name. Okay, some ghoda. Chalo. Let's see this. So, if I talk about the direction in which you have applied the load. So, direction in which you applied the load, direction of load, we say this as the longitudinal direction. This is my longitudinal direction. Which is my longitudinal direction? The direction in which we have applied the load. Next, the directions which are perpendicular to the direction of load are termed as transverse directions. So, directions perpendicular to load is termed as transverse directions or lateral directions. Right? So, due to this external load P, the length of the member has increased from L dash to L. Sir, upon tensile force. Okay. So, due to this external load P, the length has increased from L dash to L. So, in this case, I will write longitudinal strain. Longitudinal strain is equal to delta L by L, right? Whereas the transverse strains or lateral strains can be written as lateral strains can be written as delta B by B or delta D by D. These are your lateral strains, right? Now you have to take care of the directions. The longitudinal strain is elongating, right? It's positive. While the other two dimensions are getting contracted. So this is negative. This is also negative. The ratio of negative times of lateral strain to longitudinal strain is termed as Poisson's ratio. So how do we define Poisson's ratio? Poisson's ratio mu is lateral strain to longitudinal strain. Now we have to make this as positive. We know that lateral strain will always going to have the opposite sign with respect to the longitudinal strain. If the longitudinal strain is elongating, the lateral strain will be contracting. So in order to maintain the positivity, I'll just apply one negative sign, and this is how I define the Poisson's ratio. Poisson's ratio is negative times of lateral strain to the longitudinal strain. Okay. So this is the second thing. Now, my dear students, Hooke's law are also applicable for shear stresses, and it is also applicable for hydrostatic stresses. So Hooke's law for shear stresses can be defined as Hooke's law for shear stress, or you can write down Hooke's law for shear. That will be sufficient. So first of all, understand how we define shear. This is my body, right? This is my body, and I have applied a force like this over the body. This force we have applied tangentially along the surface. So this force is termed as your shear force. Shear force tau is equal to the resisting force along the surface divided by the resisting area. Shear stress tau is equal to the force along the surface divided by resisting area. Now when you have applied the force along the surface, this body will undergo deformation like this. This is the deformation that this body will undergo. This is the deformation that this body will undergo, right? And this deformation is some phi. This deformation is some phi, okay? This is delta x, and this height is h. So shear strain is defined as phi. Shear strain is defined as delta x by h. Always remember, shear strain is always measured as an angle, right? So shear strain is equal to tan phi, which is delta x by h. Now this phi is very, very small. That's why we have approximated as tan theta is equal to theta. And we can easily write phi is equals to delta x by h. Now as per Hooke's law, your shear stress tau is directly proportional to your shear strain phi. When you remove the proportionality sign, you have tau is equal to shear modulus G into phi. So this is your Hooke's law for shear. Shear stress tau is equal to G into phi, where G is modulus of rigidity or shear modulus. Okay. Similarly, we have defined the Hooke's law. Sir, is there any material whose Poisson's ratio is negative? Yes, my dear Devesh. Okay, I'll write here. If I have to write the range of Poisson's ratio, it is from -1 to 0.5. If I have to write the range of Poisson's ratio, it is -1 to 0.5. You have to understand this. When I talk about human tissues, these human tissues, if you just applied the load like this, so the other two dimension instead of contracting, they will also going to elongate. So human tissues are one of the primary examples for which your Poisson's ratio is negative. You have observed this expression? The nature of lateral strain is opposite to that of the longitudinal strain. But when the nature of both the strains are same, then your Poisson's ratio is negative. And that we have observed for the human tissues. When you extend the tissue or stretch the tissue, the other two dimension also get stretched. So that is how we define the negative Poisson's ratio. I hope I have answered this question, Devesh. Just comment yes or no. Okay, so this is the thing. Next is for hydrostatic or Hooke's law for hydrostatic Hooke's law for hydrostatic load, right? So if this is my water level and this is the body over which from all the sides equal amount of hydrostatic pressure, say sigma, is acting. So due to this hydrostatic pressure, you will find that the volume of this material will going to change. And the change in volume per unit original volume is defined as your volumetric strain. So earlier if the volume was V, now this volume has changed to some volume V dash. This is your changed volume. This changed volume is V dash, right? So volumetric strain is epsilon V is equal to change in volume per unit original volume. This is your volumetric strain. Now as per the Hooke's law, we can say that your direct pressure sigma is proportional to your volumetric strain. Or you can write down this as change in pressure is directly proportional to your volumetric strain. Removing the proportionality sign, you can write down change in pressure is equal to K into volumetric strain. And this change in pressure is equal to K into volumetric strain. Here K is your bulk modulus. K is your bulk modulus, right? K is your bulk modulus. So this change in pressure is equal to K into volumetric strain, is where K is your bulk modulus. Now my dear students, Young's modulus E, shear modulus G, bulk modulus K, and Poisson's ratio mu, all these are known as elastic constants. All these are known as elastic constants, and we have a relation among all these elastic constants. So next is the relations amongst elastic constants. What is the relation amongst elastic constants? From this section, again you will find very easy questions from in the GATE examination. And not just GATE examination, in any examination, every time they will write one or the other expression and they will ask you to either identify the expression or calculate some elastic constant. Okay, so the first elastic constant relation, first one is E is equals to 3K into 1 minus 2 mu. The first elastic constant relation is E is equals to 3K into 1 minus 2 mu. E is the Young's modulus, K is the bulk modulus, mu is the Poisson's ratio. Next one, second elastic constant relation. E is equal to 2G into 1 plus mu. What I am saying, E is equals to 2G into 1 plus mu. You have to understand from here only. You have to learn from here only. Just tell me the first expression, E is equals to 3K into 1 minus 2 mu. Second expression, E is equals to 2G into 1 plus mu. Next. E is equals to 9 kg by 3K plus G. 9 kg by 3K plus G. The third relation is E is equals to 9 kg by 3K plus G. Last one, mu is equal to 3K minus 2G. 3K minus 2G upon 6K plus 2G. Upon 6K plus 2G. So mu is equal to 3K minus 2G upon 6K plus 2G, right? So how many relations? 4 relations. First is E is equals to 3K into 1 minus 2 mu. Second, E is equals to 2G into 1 plus mu. Third, E is equals to 9 kg upon 3K plus G. Fourth, mu is equals to 3K minus 2G upon 6K plus 2G, right? Now, my dear students, usually they frame a statement like this. How many elastic constants minimum you should know to determine all the elastic constants? So, based on this, I give you one table. If the type of material is, I'll write here. So, based on the type of material, how should minimum number of elastic constant you should know? So, I'll write here type of material and number of independent elastic constants. Number of independent elastic constants. Number of independent elastic constants, right? So first type of material, our favorite, the first type of material is isotropic material. For isotropic material, you have clearly seen that four expressions are there, four elastic constants are written in front of you. If you know any two, you can determine the other two. For isotropic material, the minimum number of independent elastic constants are 2. For orthotropic material, what are orthotropic material? Orthotropic materials are those materials for which the material properties are same along the mutually perpendicular direction. Orthotropic material, the number of independent elastic constants required are 9. Next one is anisotropic material. Anisotropic material are those materials for which the material properties are different in all the directions. In all the directions, the material properties are different. For anisotropic material, the number of independent elastic constants required are 2. From the table given in this board, you can surely expect a 1 or a 2 mark question in your examination. This is one of the most important thing, right? Not just in GATE, I am talking about all the examinations. Whether it can be engineering service examination, whether it can be SSC JEE examination, AE JEE examination, everything very important right now. E is equals to 3k into 1 minus 2 mu is equals to 2g into 1 plus mu is equals to 9kg upon 3k plus g. Mu is equals to 3k minus 2g upon 6k plus 2g. And next, number of independent elastic constants required for isotropic material 2, orthotropic 9, and isotropic material is 21. Chalo, moving on with this. We move to the very next question of the session. Please attempt this. This is a GATE question which was asked in the examination. I am directly giving you the feel how the questions are framed. We started from a very basic question. And now we are moving towards a bit of leveled question, right? Just observe this. Again, I'll give you a 2 minute of time. Sorry, just 1 minute of time. You have to solve this and tell me the answer. Go for it quickly. And your time starts now. This session will also going to help you to analyze your speed of question solving. Do it quickly. Quickly do it. Thank you, Pragya sir. Please quickly do it. Please comment your answer. I'll be waiting for your answer. Please do the comments. Tell me which portion will going to have the maximum value of tensile stress. Please tell me that. Which portion will going to have maximum value of tensile stress? Just tell me that. Okay, let's see this question. Near fixed end, sir, 2.5 kilonewton per mm square for the portion, okay, near this end, okay. So I just name this as, this is my portion A. Okay, so this is A, this is B, and this is C, right? Now they will just tell me which portion, AB or BC? Maximum tensile stress, okay, value. AB or BC, I think you are talking about AB. Okay, let's see this. So in this question, a hanger is made of 2 bars of different sizes. Each bar has a square cross section, first of all. Each bar has a square cross section. So only you require this dimension. The hanger is loaded by 3-point loads in the mid-vertical plane as shown in the figure. Ignore the self-weight of the hanger. What is the maximum tensile stress in Newton per mm square anywhere in the hanger without considering the stress concentration effect? Whenever these type of questions are there, very good, Divesh, correct answer. Let's see. Whenever these type of questions are asked, my dear student, the first thing that you have to do is you have to remove the portion, draw the free body diagram and then analyze. Okay, so I'll start with this. I'll start with this portion BC over which you have a 50 kilonewton load acting downward. So over this section, this portion AB will apply equal and opposite 50 kilonewton load so that this body is under the state of static equilibrium. So for this portion BC, this is my state. For this portion BC, I have a load of 50 kilonewton. This is my portion BC. A 50 kilonewton load is acting like this. This is 50 and this is also 50. Now most of you have this confusion why this is 50. My dear, we have to keep this system under the state of static equilibrium. So if entire system is under the state of static equilibrium, even the portion of that will be under the state of static equilibrium. Okay, so observe this. So this is a square cross section. The area can be calculated as side into side. So side is 50 mm. So I will calculate this. This is my BC. So stress in member BC is equal to load, which is 50 kilonewton. So 50 into 10 raised to power 3 divided by area, which is 50 into 50. Okay, so this will come out as Newton per mm square. Just cross check this. So this is 50 kilonewton divided by 50 mm into 50 mm. So sigma BC, this is how much? Sigma BC, this is equal to, so this 50 cancels out. You have 1000 divided by 50. So this will be 20 Newton per mm square. Please check on this. 20 Newton per mm square, sigma BC. Devesh, you were telling 2.5 kilonewton per mm square? Okay, you are telling in kilonewton. Okay. So this is 20 Newton per mm square. Next, for the portion AB, this is my portion AB. For this portion AB, the total load acting will be 50 plus 100 plus 100. So this total will be 250. So the total load acting over this portion BC is 250 kilonewton. So equal and opposite support reaction you will have. So this will be 250 kilonewton. Right? Side is 100 mm. This is 100 mm. So we can easily calculate the stress for this portion AB. So stress in portion AB is equal to external load divided by the area. So stress in portion AB is equal to load. Load is how much? Load is 250 into 10 raised to power 3 divided by 100 into 100. Okay. So this is 1000, 10,000 and that can be cancelled by the denominator. So sigma AB is 25 Newton per mm square. 25 Newton per mm square. Now Devesh, this is the thing that you should take care in your examination as well. In which units you are asked to calculate the stresses, right? You have calculated the stress in kilonewton per mm square. But in the question, it was clearly mentioned that you have to calculate the stress in Newton per mm square. Okay. So these kind of silly mistakes try to avoid, because even after solving the question correctly, just by committing these silly mistakes, your entire solution will be wasted. Okay. So you can clearly observe that stress in member AB or portion AB is 25 and for portion BC is 20. So maximum tensile stress will happen in the portion AB and that value will be 25 Newton per mm square. So I will write here maximum tensile stress will happen on portion AB. On portion AB, and the value will be 25 Newton per mm square. This is your maximum tensile stress, right? Okay. Very good. Chalo, very good. So this is the thing right now. We were talking about the maximum tensile stress and how to calculate it. Okay. So let's move on with this. Okay, before this, just check this question. Okay, this is a very, very good question, my dear students. Just read this question. Again, this is a gate question. I'll give you 1 minute of time. I'll give you 1 minute of time. You have to use your brain and then you have to tell me which is the correct answer. The diagram is given in the next slide. You can just note down the important points right now and tell me when I should switch to the diagram, okay? Just tell me when I should switch to the diagram. You can just comment. Please comment when I have to switch to the diagram. Take 1 more minute, take 1 more minute, read the question, solve it, take 1 more minute. Go for it, go for it. It's a very good question. Switch it, sir. Okay, so this is the diagram. You can take the screenshot, Devesh. Just take the screenshot. This is the diagram. 3 bars, PQR. There is the gap. Go for it, go for it. It's a very, very good question. It's a very good question, right? Okay, let's see this. The question says that a rigid, uniform, weightless, horizontal bar is connected to 3 vertical members PQR as shown in the figure, not drawn to the scale. All 3 members have identical axial stiffness. Okay, please observe this line. All the 3 members have identical axial stiffness. And the stiffness is given as 10 kilonewton per mm. It means that if the bar has to undergo 1 mm deformation, the amount of load required is 10 kilonewton. So I hope you understand. Please reply me yes or no. Have you understood this or not? If the bar has to undergo 1 mm deformation, the amount of load required is 10 kilonewton. Please confirm this, whether you have understood this or not. Now, with this, the lower ends of the bar P and R rest on the rigid horizontal surface. When no load is applied, a gap of 2 mm exists between the lower ends of bar Q and the rigid horizontal surface. When the vertical load W is placed on the horizontal bar in the downward direction, the bar still remains horizontal and gets displaced by 5 mm in the vertically downward direction. The magnitude of this load W is. So, chalo, I'll explain this in a very simple way. This is the bar right now. You have applied a load of W over this bar. This is the load you have applied. This is the load W that you have applied. Now, due to this load W, this bar undergoes a deformation of 5 mm. This bar undergoes a deformation of 5 mm. Means, not deformation, this bar moves down to 5 mm. Now this is the new position of the bar. This is the new position of the bar, right? Now just tell me, this bar P is undergoing how much deformation? What is the deformation of the bar P? Deformation of bar P. Deformation of P. Please tell me what is the deformation of P? Deformation of P is 5 mm. Okay? Deformation of P is 5 mm. Similarly, tell me what is the deformation of R? What is the deformation of R? Devesh, this was the bar initially, right? It has moved down by 5 mm. So this P is contracted by 5 mm. Yes or no? This P is contracted by 5 mm. Please tell me yes or no. This P bar and this R bar is contracted by 5 mm. Similarly, the deformation of R. Deformation of R is also 5 mm. Deformation of R is also 5 mm, right? This deformation of R is also 5 mm. Now observe this bar Q. Below this bar Q, there is some gap. And this gap is how much? This gap is given as 2 mm. The gap below this point Q or bar Q, this gap is 2 mm. Okay. Now, if I have to talk about the deformation of this Q, the net deformation of this Q will be 5 minus 2 because this 2 mm is the gap. So, deformation of Q will be 5 minus 2, that is 3 mm. So this is the deformation of bar P, R and Q. Now the amount of load required to cause deformation in bar P is P1. The amount of load required to cause deformation in bar R is P2. And the amount of load required to cause deformation in this bar Q is say P3, right? This is the amount of load which is required to cause deformation in P, Q and R. So what is the value of P1? P1 is the amount of load required to cause 5 mm deformation in bar P, and that will be deformation multiplied by their axial stiffness, which is given as 10 kilonewton per mm. So for bar P, if I have to cause 1 mm of deformation, the amount of load required is 10 kilonewton. So in order to cause 5 mm deformation, the total amount of load required is 50 kilonewton. Next, load P2. The amount of load required to cause 5 mm deformation in bar R is again 5 into 10. So this is 50 kilonewton. Next, the amount of load required to cause 3 mm deformation in this bar Q is equal to 3 into 10. And this is equal to 30 kilonewton, right? Now the total load that you have applied is W, which has been distributed into bar P, Q and R and has caused this deformation. So this total load W is equal to P1 plus P2 plus P3. P2 plus P3, and this will come out to be 50 plus 50 plus 30, that will be 130 kilonewton. This is my final load. 130 kilonewton is my final answer. The total amount of load required to cause 5 mm deformation of this bar or 5 mm movement of this bar is 130 kilonewton. Very good, Deepesh. Correct answer. So I hope you understood this. Let's move on. Let's move on with this. Let's move on with this. Chalo. So we have discussed about elastic constants. We have seen the relation amongst elastic constants, right? Great question, great question. We will see so many great questions, Divesh. Just stay connected. Okay. So the thing is, we have seen about different types of elastic constants. We have talked about stress strain. What are the relation between stress strain, actual strain, engineering strain, all those things we did. Right. Now next we move on to the stress strain curve. Next topic of discussion is the stress strain curve of mild steel. Next we move to the stress strain curve of mild steel. Okay. Now observe this. I hope you already know about the stress strain curve, but some points you should always keep a check. So let me draw the stress strain curve for mild steel again. So this is my x-axis, sorry, y-axis, and this is my strain axis. So here I will plot the strain and here I will plot the stress. Okay. Just before beginning this, one simple thing. In the material, when you apply the load, first strain will going to happen, and in order to resist that strain, the stresses are produced. That's why the strain is always considered as an independent quantity and stress is always a dependent quantity. That's why we write down stress as a function of strain. Stress as a function of strain. Okay. So always remember, strain is your independent variable. Strain is always independent and stress is dependent on strain. Now, when you start applying the load over the body, initially your stress is directly proportional to your strain and your Hooke's law is valid, and you get the first initial portion of the stress strain curve. You will get the first initial portion of your stress strain curve. This is your first initial portion, right? From here we started. This is my point A. And A is known as the proportionality limit. What is the important thing about A? Till point A, your stress is directly proportional to strain. Now beyond point A, and also this portion is linear. Beyond point A, you will get a non-linear portion till point B. B is known as your elastic limit. This portion AB is non-linear, right? This portion AB is non-linear. This portion AB is non-linear. After this, you have the upper yield point and the lower yield point. So I'll draw it like this. This is point B. This is point A. This is point B. And this portion AB is non-linear. Then you have this upper yield point C dash. And due to the slippage of carbon atom, you see the fall in stress. And this is your lower yield point C, right? From C, at constant stress, you see huge amount of deformation happening. And this CD is termed as your yield plateau. Okay. Due to the reorientation of the molecules of the crystal structure, now the material can restrain more amount of load. The material can offer extra amount of resisting force, due to which you see this strain hardening zone DE. This is the strain hardening zone DE. And why this strain hardening zone is there? This strain hardening zone is because of the extra resistance offered by the material due to reorientation of the crystal structure. Then you have this point E, which is known as the ultimate load point. And after this, if you keep on loading the substance, the necking will going to start. That is, the reduction in cross-sectional area will going to start. And beyond this point E, you have the necking zone. And at point F, you will see the failure of the material, or more precisely, the shear failure of the material. So this is your necking zone. This is your necking zone. This is your strain hardening. This this is your yield plateau. Okay. Now, 2-3 basic things you have to take care. First of all, till point B, your material is elastic. Means if you remove the load, the material will going to regain its original shape and size. So the strain corresponding to point B, this strain is known as your elastic strain. Up till this point, whatever strain you will get, this is known as your elastic strain. Okay. Beyond this point B, the deformations are permanent. So whatever strains you will get are counted as your plastic strain. So starting from this point till the strain you will get at the fracture point, this is known as your plastic strain. This is known as your plastic strain. Okay, I'll just mention this more clearly. This is your plastic strain and this portion is your elastic strain. Reason of being elastic strain, because if you remove the load, the material will going to regain its original shape and size, right? Now, when we talk about the yield strength of the material, especially the ductile materials, the yield strength of the material is always measured to this lower yield point, C. This is the yield strength of the material. It is always measured to the lower yield point C. So I'll write down here, sigma y is the yield strength. And yield strength is always measured with respect to your lower yield point, right? So these are the primary things about your stress strain curve. Now, one important thing related to this is, my dear students, how do you define the material is ductile? Rishikesh, sir, concept DNA में जा रहा. Thank you. Just stay connected. DNA से RNA और सब जगह पहुंच जाएगा आपके एग्जाम तक. ये मेरी गारंटी है. चलो, मूवते हैं आगे. Next is, I was talking about the ductile material. How do you define the material is ductile? How do you define that the material is ductile, right? Now, in order to define the material, ductility of the material, usually what we see, how much elongation is happening, all those things. But I'll give you the scientific definition. The scientific definition is, a material is said to be ductile if their post-elastic strain or plastic strain is more than 5%. If your plastic strain, is more than 5%, then the material is said to be ductile. The most scientific definition of the ductility of the material. If the post-elastic strain or the plastic strain is more than 5%, then only the material is said to be ductile. Okay. This you should keep a check. Now, next thing about this stress strain curve is, we have talked about ductility, we have talked about the plastic strain. Okay, now, next. There are some ductile materials for which this yield point is not visible. For that, we go with the proof stress. So, I'll just draw this quickly. So, this is my stress axis. This is my strain axis. This is, okay. If this is the stress strain curve for a ductile material, right? Then how to determine which point is the yield point? Okay. Now, in order to determine the yield point for such material, what we do is, we take an offset for aluminium, we take an offset of 0.02%. We take an offset of 0.02%. Means this is the strain, right? This is the strain and this is your stress. We take an offset of 0.02%. Means at the strain of 0.02 at this point, percent, we draw a line which is parallel to the initial portion of this curve. So this is how we draw a line which is parallel to the initial portion of this curve. And the point where this offset line intersects with the stress strain curve, this point is termed as your yield point. This point is termed as your yield point, and the stress corresponding to this point is known as your yield stress, which is also termed as your proof stress. This is termed as your proof stress. I will just write down sigma p. So what I am saying that for ductile materials for which yield point is not clearly visible, we'll take an example of aluminium. For aluminium, the yield point is not clearly visible. Then for aluminium, we take an offset of 0.02%. We draw a line or we draw an offset parallel to the initial portion of the curve. And where this offset will going to cut the stress strain curve, that point is considered as the yield point. And the stress corresponding to that point is marked as your proof stress. So sigma p is your proof stress. Sigma p is your proof stress. Okay. So this is the thing. So these are the important things about stress strain curve. Now usually, my dear students, what they give is they give two line curve. Okay. And they will ask you which type of material is this. So let's see that also. So stress strain curve for different types of material. Stress strain curve for different materials. Stress strain curve for different materials, right? Now we'll start one by one. Okay, I'll just draw like this. If this is the stress strain curve given to me, where you have only one line like this, okay? So always remember this, a single line like this tells me that Hooke's law is valid. And whenever Hooke's law is valid, it means that your stress is directly proportional to the strain and the material is said to be elastic. So when you have a single line like this for stress strain curve, this is your stress strain curve. So this type of material is termed as your elastic material. Okay. Next, if you are given with a stress strain curve like this is your, and then this is the curve given to you. This is again the stress strain curve given to you. Now in this stress strain curve, you can clearly see this is your elastic region where stress is increasing with strain. And this is your plastic region where yielding is shown to you. So this is known as elastoplastic. Elastoplastic material. Next, if a curve is given to you like this is your linear part, and then you have like this. So here you can clearly see that in this initial portion is the elastic portion. Beyond elastic portion, you have a plastic portion, and in that plastic portion, you are also seeing some amount of strain hardening. So this is elastoplastic with strain hardening. This material is elastoplastic with strain hardening. This is elastoplastic with strain hardening. So first material elastic, elastoplastic, then elastoplastic with strain hardening. Very good, Deepesh. Now next, moving on with this. Next you have a material like this. You have a material like this, right? And for this material, this is the stress strain curve given to you. This vertical line. This is your strain, this is your stress. Now from this, you can clearly identify that no matter whatever load you have increased, you are not getting any strain. When your body is not deforming at all, then that body is termed as the rigid body. So this is the stress strain curve for a rigid body or for a rigid material. Next you have the stress strain curve like this. This is your stress strain curve, and you are given with a curve like this. This is strain and this is your stress. Okay. Now you can observe this from this diagram clearly that even the small amount of stress is producing huge deformation. Even the slightest of the stress is producing huge deformation. This we have seen in the fluid case. So this is your ideal fluid. This is your ideal fluid. This is your ideal fluid. This is rigid. Now last one is, if you have the stress strain curve like this, and for that stress strain curve, this is the curve given to you. Only and only yielding region is given to you. Sir, whether ideal solid and rigid body are the same. Devesh, better you call it as rigid, right? Because we are talking about solid bodies only. Rigid bodies are those bodies, means the clear-cut definition that I should give to you is, rigid bodies are those bodies for which you will get negligible deformation or no deformations at all. In this case, you are not getting any deformation, doesn't matter whatever stress you have applied or whatever load you have applied. So this is termed as your rigid body. Instead of solid body, start calling it as a rigid body. Okay. Now in this stress strain curve, you are only given with this yield plateau. And you know this yield plateau will always come in the plastic region or the plastic zone. So this body is termed as ideally plastic. This is termed as ideally plastic. This is termed as your ideally plastic. So these are some of the common stress strain curve that you should keep in mind. All these 6 curves are important. In many examinations we have seen the questions are framed from all these 6 types of curves. Okay. Chalo, this is the thing. Now next we move on to the very, very important topic of stress tensor. Stress tensor. We move on to a very, very important topic of stress tensor. Now observe this. So this is the element I have considered. The directions are like this. This direction I will consider it to be x. I will draw here. This direction will be my x direction. This will be my y direction. And the direction coming out of the board, this direction will be my z direction. Okay. Now tensors are those quantities for which 2 directions are defined. Okay. Tensors are those quantities for which 2 directions are defined. You have seen this. We write down stress like this. Stress is a tensor quantity. First one is the direction of plane and second one is the direction of force that will cause that amount of stress. Okay. So this is the body that I have given. First one is sigma xx. Sigma xx will tell me in this, the first x will tell me the direction of plane over which this stress is coming, and second x will tell me the direction of force that causes this stress. So if I apply a force along x direction, that will going to produce the normal stress on the plane, on this plane, right? And this is what plane? This is your x plane. The direction of any plane is defined using the normal of this plane. So normal of this plane is along x direction. So this is sigma xx. Similarly, this is your sigma yy. What is sigma yy here? Sigma yy is the normal stress acting on the y plane due to the force acting along y direction. Similarly, you have this sigma zz. This is your sigma zz, right? Sigma zz is the normal stress acting on the z plane due to the force along z direction. Next, you have shear stress. This is your tau xy. This is your tau xy, right? Now, in this shear stress tau xy, This shear stress is acting on which plane? It is acting on x plane. Due to the force acting along y direction, you will get tau xy. Similarly, this is your tau yx. This is your tau yx. And how we are defining tau yx? Tau yx is the shear stress acting on the y plane due to the force acting along x direction. Okay, similarly, this is your tau xz. Shear stress acting on the x plane due to the force acting along z direction. This is your tau zx. Shear stress acting on z plane due to the force acting along x direction. This is your tau yz. Shear stress acting on y plane due to the force acting along z direction. And this is your tau zy. So shear stress acting on z plane due to the force acting along y direction. So stresses are always defined in terms of tensor. So stress is a tensor quantity for which you have two directions. First is the direction of the plane. This sigma, if I write this stress as sigma xx. So this first is the direction of plane over which this stress is acting. And second one is the direction of force causing this strain or causing the stress. This is how we write the stress tensor, right? Now we will write the stress tensor. So stress tensor is equal to it's a 3 cross 3 matrix, sigma xx, tau xy, tau xz. Then you have tau yx, sigma yy, tau yz. Then you have tau zx, tau zy. Then you have sigma zz. So this is your stress tensor, right? Based on this stress tensor, I can write down the strain tensor. So strain tensor is you have epsilon xx, then you have phi xy by 2, then you have phi xz by 2, then you have epsilon you have phi yx by 2, you have epsilon yy, then you have phi yz by 2. Last, you have phi zx by 2, you have phi zy by 2, you have epsilon zz. So this is your strain tensor. Using this stress and strain tensor, you can calculate the different quantities, right? So these are your stress and strain tensor. Now next we will going to see how we will going to write down the stresses. So this is the thing, right? This is your sigma x. This is your sigma y. And this is your sigma z. Okay. Now I want you to write down the strain along x direction. So strains along x direction, epsilon x is equal to sigma x by e, right? This sigma x will going to elongate the member. Then you have the Poisson's effect of sigma y and sigma z. sigma y is elongating the member along this direction, y direction, so it will going to contract the member in the other two direction. So minus the Poisson's effect of sigma y by E, minus the Poisson's effect of sigma z by E, right? How I have written the strain along x direction? So first of all, I have taken sigma x minus the Poisson's effect of sigma y and sigma z. Similarly, I will write down epsilon y is equal to sigma y by E minus the Poisson's effect of sigma x minus the Poisson's effect of sigma z. Okay, then I write down epsilon z is equal to sigma z by E minus Poisson's effect of sigma x minus Poisson's effect of sigma y. So minus mu times of sigma y by E. Now when you add these three strains, you will get the volumetric strain. So volumetric strain epsilon V is equal to epsilon x plus epsilon y plus epsilon z. This is your volumetric strain. When you add these three terms, you will find that your volumetric strain is equal to sigma x volumetric strain epsilon V is equal to sigma x plus sigma y plus sigma z into 1 minus 2 mu divided by E. A very, very important relation. Epsilon V is equals to sigma x plus sigma y plus sigma z into 1 minus 2 mu divided by E. Okay. Now can you tell me, if I say volumetric strain is 0, if I say volumetric strain is 0, if volumetric strain is 0, if volumetric strain is 0, then either the sum of the stresses is 0. If volumetric strain is 0, then the first condition is sum of the stress sigma x plus sigma y plus sigma z is equal to 0. This is the first situation. So many times they ask you to calculate the volumetric strain. Now, before calculating the volumetric strain, please check this. If the sum of sigma x, sigma y and sigma z will be 0, that will going to save a lot of your time. Because if this is the condition, then your volumetric strain will be 0. Next, if your volumetric strain is 0, then 1 minus 2 mu should be equal to 0. And from that, mu comes out to be 0.5. Mu comes out to be 0.5. So these are the two conditions for which your volumetric strain to be 0. I tell you one thing. Mu is 0.5 for incompressible material. And we can understand from here as well, if volumetric strain is 0, it means that the change in volume is 0. And change in volume is 0 for an incompressible material. So especially for this, for mu is equal to 0.5, we say that the material is incompressible. For mu is equal to 0.5, we say that incompressible material. Incompressible material. So next time, if you are given with an incompressible material, you can directly take mu is equals to 0.5. Okay. So this is the condition. This is how we write down your stress strain. Now from here, you can also calculate one more thing. That is your sigma x is equal to E upon 1 minus 0.5 mu square. Sorry, E upon 1 minus mu square. E upon 1 minus mu square into epsilon x plus mu times of epsilon y. This is again a very, very important relation. sigma x is E upon 1 minus mu square into epsilon x plus mu times of epsilon y. Next is the differential form of strain. Differential form of strain. If the change along x, y and z direction, I'll write here, change along x, y and z is u, v and w, then your longitudinal strain or epsilon x is equal to del u by del x, epsilon v or epsilon y is equal to del v by del y. Okay, and if you need to calculate phi xy is equal to del u by del y plus del v by del x. Okay, so epsilon x, epsilon y, phi xy. Similarly, you can calculate epsilon z also. Epsilon z is equal to del w by del z, and also you can calculate phi yz, which is equal to del w by del z plus, this is del u v, so del v by del z plus del w by del y. Similarly, you can calculate phi xz, which is del u by del z plus del w by del x. Okay, so this is the thing. So these are the differential forms. Now we will continue with the question. So let's start with this. Okay, you have 2 minutes of time. Just go for it. It's a very, very good question. Just go with this. So let's see this question. Question says that a rigid bar is suspended by 3 rods made of the same material as shown in the figure. The area and length of the central rod are 3A and L. This is the central rod. Area is 3A and length is L. Respectively, while that of the other two outer rods are 2A and L. 2A and this is 2L. This is also 2A and 2L. Okay. If a downward force of 50 kilonewton is applied to the rigid bar, the forces in the central and each of the outer rod will be. Okay. So this is the situation given to you. This is the bar over which you apply the 50 kilonewton load. Now, my dear students, you can clearly see if you apply the 50 kilonewton load over this bar will going to settle like this. This bar will going to settle like this. This is the new settlement of the bar. Okay, this is the settlement of the bar. This is the delta for the bar. This is the delta for the bar, right? Now, this deformation is same for the outer bars and also for the inner bar. The deformation delta is same for the outer bar and the inner bar. So I am writing like this. Due to this deformation, the stress or the load that this bar will undergo is load P1 and this load is P2 and this is P3. Under the action of these loads, these bar will going to deform by the amount of delta. I'll write like this. Deformations for outer bars is delta. Therefore, since area is 3A and length is, area is 2A and length is 2L, due to which, and they are also made up of same material. Therefore, we can say that the load which is required to cause this deformation delta will also be same. So from that I can write down P1 is equal to P3. Okay. The load which is required to cause the deformation delta will also be same. P1 is equal to P3. Now what is this deformation in the outer bar? So deformation in this outer bar delta is equal to P1 into L, which is 2L, divided by A into E. So A is 2A and E is how much? E is given to us. E is, I think, okay, we take it as E. This is the deformation in the outer bar. Okay. Similarly, I can write down deformation in the middle bar is also delta, and this is equal to P2 into L divided by 3A into E. Okay. Now these two deltas are same, so I can equate these two delta. So I can write down P1 into 2L divided by 2A into E is equal to P2 into L divided by 3A into E, right? So from here the value of P1 comes out to be P2 by 3. So P1 is equal to P3, P1 is equal to P2 by 3. Next is, you can write down P1 plus P2 plus P3 is equal to 50 kilonewton. So P1 plus P2 plus P3 is equal to 50 kilonewton. So instead of P3, I will write P1, and instead of P2, I will write down 3 times of P1. So this is 3 times of P1 plus P1 is equal to 50. So this is how much? 5 P1 is equal to 50. So P1 comes out to be 10 kilonewton. This is the value of P1. From here the value of P2 is 30 kilonewton. Just cross check the answer. And the value of P3 is also 10 kilonewton. Just cross check this answer once, whether we have committed any mistake or not. Just cross check this once. So P1 is equals to 10 kilonewton, P2 is equals to 30 kilonewton, and P3 is equal to again 10 kilonewton. So this is how we will going to calculate the forces for all these members. Chalo, moving on with this, let's try this one. This is the question for ratio of elongation of the prismatic bar due to its total self-weight W to that of a similar bar with an additional weight W. Okay. So before this question, I would like to tell you one thing. If the bar is hanging under its self-weight, if the bar is hanging under its self-weight like this is the bar hanging under its self-weight. Length of the bar is L, unit weight of the bar is gamma, then deformation of the bar under its self-weight delta is equal to gamma L square divided by 2E. This is the deformation of the bar under their self-weight. Okay. Now the same thing can be written as delta is equals to WL divided by 2AE. Where W is the total load of the bar. The total load of the bar is W. WL divided by 2AE. Now this W is nothing but gamma into A into L. That is the total load. So deformation under the self-weight is this. So I will write down deformation under self-weight. Deformation under self-weight. Deformation under self-weight is delta is equals to gamma L square divided by 2E. Now just go for this question. The question says that the ratio of elongation of the prismatic bar due to its self-weight W to that of a similar bar with an additional load W attached at its free end is. Okay, so this is the deformation of the bar under its self-weight W. Now the next one is you have a bar like this. You have a bar like this. This is the bar. This is the bar. For this bar, the total load is W and also an additional load W is hanging here. For this bar, the total deformation delta dash is equal to, first of all, deformation under the self-weight W is WL by 2AE plus deformation due to this load W, which is equal to WL by AE. This is the deformation under self-weight. This is deformation under self-weight. And this is due to external load W. You are asked to calculate the ratio of delta to delta dash. Just do the calculation and tell me the answer. The deformation of the bar under self-weight W is WL by 2AE. The deformation of the bar in which self-weight is also considered and this load W is also considered is this much. Just calculate this. So this will be 3WL by 2AE. So this is your delta dash, right? 3WL by 2AE. Now you have to simply take the ratio of delta to delta dash. And when you take the ratio of delta to delta dash, your answer will be your option A. So for this question, your option A is the correct answer, which is 1 by 3. Okay. Have you understood this? Just comment yes or no. Have you understood this or not? Just comment yes or no. Just tell me, have you understood this or not? Please tell me yes or no. Okay, let's move on to the next question. This is the next question for your bar under the self weight. Just answer this. You have again 1 minute of time. Just go for it. It's a very easy question. Chalo, take 2 minutes. Answer this. It's a trick question, by the way. Please tell me the answer for this question. It's a very good question, by the way. Please tell me the answer for this. Okay, let's see this question. The question is saying that a bar of length L is weighing W per unit length, hangs vertically and carries a load of W at its free end of the bar. The tension force in the bar at a distance x from the support is. The bar of length L is weighing W per unit length, hangs vertically and carries a load W. Okay, let's see this. This is your bar. This is hanging vertically. And it is also carrying a load W at its free end. The load per unit length is small w given to us. The tension force in the bar at a distance x from the support. Say this is the section which is situated at some distance x from the support. And you need to find out what is the tension force that will be there in this bar. At this section xx, what is the tension force? Okay. Now you observe this. The tension force at this section is the weight of this portion, and the weight of this portion is, this length is L minus x. This length is L minus x. So weight of this portion, so tension force in section XX is equal to weight of hanging portion plus load W. What is the weight of hanging portion? Weight of hanging portion is W, which is the weight per unit length. This is the weight per unit length. W into L minus x plus W. So this is your tensile force acting at this section XX, which is W into L minus x into capital W. So for this question, your option B is your correct option. Okay, so this is an easy one. Let's go with the next question. This is the next question. Just attempt this. Now this one is a trick question. So better you go with this question, keeping your consciousness alert. I'll give you just 1 minute of time. Quickly go with this. Quickly go with this question. commenting your answer, right? Keep commenting your answer in the chat box, and please share this session to the maximum people. All those of you know, just keep sharing this session. Okay, let's see. A uniform steel rope is equals to 2 into 10 raised to power 5 Newton per mm square and density 7.8 gram per centimeter cube of total length 40 meter hangs vertically. The ratio of elongation of the first 10 meter to that of first 20 meter would be. Now, my dear students, when most of you see this question, you just start doing I don't know what, and you just waste so much of time in these type of question. Okay. So this can be termed as a time waster for your exam. So let's see how to deal with this time waster question in 2 steps. So first thing is, what the question is saying, that a bar is hanging. The total length of the bar is 40 meters. Okay. The total length of the bar is 40 meter. What will be the ratio of elongation of first 10 meter to that of first 20 meter? Whenever such type of questions are asked in the examination where you need to calculate the ratio, it is always suggested to go with the proportionality. Okay, now what I am saying is, if I talk about deformation under self-weight, it is gamma L square divided by 2AE or 2E. Gamma L square divided by 2E. Now from here I can say that your deformation delta is directly proportional to the length of the hanging portion. Length of hanging portion. The length of hanging portion, the whole square. Your deformation delta is directly proportional to the length of hanging portion, the whole square. So if I have to calculate the deformation at first 10 meter, this is the first 10 meter. So what is the length of hanging portion? The length of hanging portion will be 30 meters. So my delta 1 will be directly proportional to 30 square. Okay. Now next, for the first 20 meter, this is the first 20 meter. This is the first 20 meter, right? This is your first 20 meter. For first 20 meter, the length of hanging portion is 20 meter. So delta 2 is directly proportional to 20 square. So you have to just take the ratio. Delta 1 by delta 2 is equal to 30 by 20 the whole square. So this comes out to be 9 by 4. Directly in one line. This comes out to be 9 by 4. So for this question, your option D is your correct option. Now the same question can waste so much time in your examination. You start calculating the elongation for first 10 meter, and then you start calculating the elongation for next 20 meter, and then you will don't know what you have calculated. So in one step, your deformation is directly proportional to the length of hanging portion, the whole square. More the length of hanging portion, more will be the deformation. Okay. So you can use this proportionality and you can directly take the ratio of delta 1 by delta 2. What is delta 1? Delta 1 is the elongation of the first 10 meter length of the bar under self-weight. Delta 2 is again the elongation of first 20 meter of the bar under its self-weight. Okay, I hope you understood this. Chalo, moving on with this. Let's see this question. Next one. Again, I'll just give you 1 minute of time. It's a good question, so try to solve it quickly. It is based on the differential form of strains. Please go for it. Time's up. Let's see this. The question is saying a 2D thin plate with modulus of elasticity E is equal to 1 Newton per meter square. I'll just keep on writing. E is 1 Newton per meter square. Next, Poisson's ratio mu is 0.5 is in the plane stress condition. The displacement field in the plate is given as U is equals to Cx. U is, mu is 0.5. U is given as Cx square y. V is 0, where U and V are the displacement along x and y directions. Next, C is the constant in per meter square. The displacement x and y along capital X, capital Y respectively are in meters. The stress in the x direction is sigma xx, which is 40 xy. So sigma xx is 40 xy Newton per meter square. Okay. Next. The shear stress tau xy is alpha x square. Then what is the value of alpha? Tau xy is alpha x square. Then what is the value of this alpha? That you need to calculate, right? Now, my dear students, in order to get the value of alpha, first we need to determine the value of this constant C. Now, just see how we determine this. So, sigma xx is equal to E upon 1 minus mu square into epsilon x plus mu times of epsilon y. Okay, so this is the relation that we have studied. Now observe this. This E upon 1 minus mu square, this epsilon x can be written as del u by del x plus mu times of del v by del y. Okay, this you can do. Now substitute the value of u, which is given as cx square y. So you have E upon 1 minus mu square into del by del x of cx square y plus 0, because the value of v is 0, so that will be 0. So I will write this as E upon 1 minus mu square into 2 times of cxy, and this is equal to your sigma xx. So sigma xx is given as 40 xy. So I will write down 40 xy is equal to E, which is 1, mu is 0.5, so 1 minus 0.5 square into 2 times of C into xy. Okay, so this xy and this xy will going to cancel out. Just get the value of C quickly. Do the calculation and tell me the value of C. So C will come out to be 15. The value of C will be 15. The value of C is given as 15. Okay. Now next thing is how to relate this shear stress. So shear stress can only be related with shear strain. So for relating that, I have to first calculate the value of phi xy. So phi xy is equal to del u by del y plus del v by del x. This is the value of phi xy. So this is equal to del by del y of cx square y plus 0. So phi xy is equal to cx square. Now c we have calculated as 15. So phi xy is equal to 15x square. This is the value of phi xy. Now shear stress and shear strain is related using the shear modulus. So first we need to calculate the shear modulus. So for calculating shear modulus G, I can use a relation E is equals to 2G into 1 plus mu. Okay, so E is 1, G I need to calculate into 1 plus 0.5. So 1 plus 0.5 will be 1.5. 1.5 into 2 will be 3. And the value of G comes out to be 1 by 3. The value of G is 1 by 3. So G I know the value of shear stress, I know the value of shear strain. Then I can apply the Hooke's law to get the value of alpha. So by Hooke's law I can write shear stress tau xy is equal to G into phi xy. Tau xy is given to us as alpha x square. So this can be written as alpha x square is equal to G, which is 1 by 3 into phi xy, that is 15x square. So this is 15x square, right? This x square will going to cancel out. 3 ones are 3 5s are. So the value of alpha comes out to be 5. So this was our answer for this question. So the value of alpha comes out to be 5, right? Now usually when you have these type of questions, you can start thinking backwards, okay? So this is how you need to deal with this question. Chalo, moving on with this. Next is this question. Please try this. I'll give you just 2 minutes of time. Please go for this. Okay, let's see this question. So this is the question where, okay, let's see this question. So this is the question where the bars are connected in series. Okay, all these are prismatic bar and all these bars have the same cross-sectional area. So let's see this. Question says that a mild steel bar of 20 mm by 20 mm in cross-section is subjected to axial forces as shown in the figure. If E is 2 into 10 raised to power 5 megapascal, then the change in length for the portion BC is. You need to calculate the change in length for the portion BC. Every time you get these type of questions, step 1 is draw the free body diagram. Okay. So first of all, I'll consider this portion AB. So this is my portion AB. For this portion AB, you have a 60 kilonewton load. I'll start from this. So you have a 60 kilonewton load acting like this. This is 60. So on the other hand, again equal and opposite, 60 kilonewton load should act. So this is your portion AB, right? Now talking about your portion BC. This is your portion BC. This is your portion BC. Now in order to balance this 60 kilonewton load, equal and opposite load should be acting over this face. So this should be 60. And you have a 90 kilonewton load acting on this side. So when you take the net summation, this is 90, this is 60. So net summation will be 30 and that will be acting on the left side. This is 30 and this 30 will be tensile. So equal and opposite should act on this side. So your portion BC is under the action of 30 kilonewton load, right? So just for your reference, I will draw the FBD for CD portion also. This is your portion CD, right? Now in order to keep this under equilibrium, if this portion is applying 30 kilonewton load on this, then this portion will apply 30 kilonewton load opposite in this direction. And you have 120 acting like this. So the total load acting on this portion will be 150. This will be 150. And this will also be 150, right? Now you need to calculate the elongation for the portion BC. So elongation for portion BC is equal to delta BC is equal to P, which is 30, length of this portion. So length of the portion is 1200 mm. So 30 kilonewton. So 30 into 10 raised power 3 into length PL divided by area of cross section. So this is a square cross section. Area is 20 by 20. PL by AE. So 20 cross 20 into E. So E is given as 2 into 10 raised power 5 megapascal. So this is 2 into 10 raised power 5 megapascal or Newton per mm square. So from here, you will directly get the elongation for portion BC in mm. Just do the calculation and tell me the answer for this. Please tell me the answer for this. So this 10 raised power 3 and 2 zeros, this will cancel out with 10 raised power 5. And you have 1 0 will cancel out here. So you have 36 divided by 8. 80, sorry. 36 divided by 80. So this will come out to be as 0.45 mm. This will be my final answer. So this is the elongation for the portion BC, right? Okay, chalo, moving on with this, moving on to the next question. So this is the question from thermal stresses. Please try this. I'll give you just 2 minutes of time. Please go for it. Please go for it. go for it and tell me the answer. Please go for it. Please go for it. This is the question from thermal stresses. Okay. Okay. The question says that determine the stresses in the bar as shown in the figure if the temperature is raised by 30 degrees Celsius. So delta D is 30 degrees Celsius. First of all, when we talk about thermal stresses, okay. So before solving this question, I would like to give you some details about thermal stresses. First one is, if the bar is free to expand and you increase the temperature for this bar, then no thermal stresses will be developed inside this bar. Thermal stresses will only be developed if the bar is restrained from deformation. If you just stop the bar, you apply some support and you restrain the bar from deforming, then only the thermal stresses will come. Okay. So for here, an arrangement of copper and steel is given to you. The length of these two rods are 1.5 meter and 1 meter. First of all, okay, so here are two supports, and between these support and this, a gap of 0.03 mm is there. Okay. If this assembly is expanding more than 0.03 mm, then only the thermal stresses will be developed. Okay, so let's check this first. What is the free expansion? So free expansion is length of copper bar into alpha of copper bar into delta T plus length of steel bar into alpha of steel bar into delta T. This is the free expansion, right? If the deformation is more than 0.03 mm, that is the gap, then only the thermal stresses will be produced. So length is 1.5 into 10 raised to power 3. Alpha for copper is how much? Alpha for copper is 16.5 into 10 raised to power minus 6 into delta T. Delta T is how much? Delta T is 30 degrees Celsius into 30. So this is your free expansion for copper bar. Free expansion for steel bar is 1 into 10 raised to power 3 into alpha for steel is how much? Alpha for steel is 12.5. 12.5 into 10 raised to power minus 6 into 30 again. Okay. Just calculate this and tell me the value. Please calculate this and tell me the value. Just calculate this and tell me the value. So this is how much? 1.5 into 16.5 into 30 plus 12.5 into 30. Okay. So this is 1.117 mm. This is the total free expansion of the assembly. But the gap is 0.03 mm. Since this free expansion is more than 0.03 mm, that's why the thermal stresses will be developed. Then thermal stresses will be developed. Then thermal stresses will be developed, right? Now, say the thermal stresses developed in both the bars are compressive, although they will be compressive because this support will not allow the free expansion of the bar, due to which these type of compressive thermal stresses will be developed in the bar. This is sigma copper and this will be sigma of steel. These are the thermal compressive stresses developed in copper and steel. Okay, this is sigma steel. Okay, we need to develop these two values of sigma Cu and sigma St, which are the thermal stresses developed in the bar. Now understand this, my dear student, how we calculate this. First of all, this assembly has to be under the state of static equilibrium, means the total net force acting over this member of copper should be equal to the total net force acting over this member of steel. So first equation I'll write like this: compressive force in copper is equal to compressive force in steel. So compressive force in copper is equal to sigma Cu into area of cross section of copper. This is equal to sigma of steel into area of cross section of steel. And these two areas are given to us. This is 200 centimeter cube and that is 100 centimeter cube. So this is equal to sigma Cu into 200 is equal to sigma St into 100, right? From here I can write down sigma Cu is sigma St by 2. This is your stress in copper, sigma St divided by 2, right? This is your stress in copper. Now next one is, due to this expansion, right? Due to this free expansion, this assembly is wanting to get expanded by 1.117 mm. But actually it is only getting expanded by 0.03 mm. So net deformation is 0.03 mm. So for this I can write down net deformation for this assembly is 0.03 mm. Net deformation is 0.03 mm. Now this net deformation is free expansion of copper. It is free expansion of copper minus effect of sigma Cu. So this is for copper, right? Free expansion of copper minus effect of sigma Cu. Next one is plus free expansion of steel minus effect of sigma St. That is the thermal stress in steel. And this should be equal to 0.03, right? So this is the equation through thermal stresses I have formed. Free expansion of copper minus effect of sigma Cu plus free expansion of steel minus effect of sigma St should be equal to 0.03. Now let's see. The free expansion of copper is L of copper into alpha of copper into delta T. Okay. Effect of Cu will be sigma Cu divided by E of copper. This is the first term. The second term is L of steel into alpha of steel into delta T minus sigma ST divided by E of copper. Sorry, E of steel. And this should be equal to 0.03. This first term, L of Cu into alpha of Cu into delta T, L of St into alpha of St into delta T, this we have already calculated. This we have already calculated, which is 1.117 mm, right? So I can reduce this 1.117 minus sigma Cu divided by E of Cu minus sigma St divided by E of St is 0.03. Okay. Now we know about this E of steel, which is 2 times of E of copper, which is 200 gigapascal. So E of steel is 200 gigapascal, E of copper is 100 gigapascal. And sigma Cu is 2 times of sigma St. So I'll just substitute this. So this is 1.117 minus sigma Cu can be written as 2 times of sigma of steel. E of Cu can be written as 100 gigapascal. So 100 into 10 raised to power 3 Newton per mm square. Okay. Minus sigma St divided by 200 into 10 raised to power 3 Newton per mm square, and this should be equal to 0.03. From here you can calculate the value of sigma St in Newton per mm square. Just take out sigma St common. So you have 1.117 minus 0.03. This is equal to, this will be how much? This is 4 plus 5 times of sigma St divided by 200 into 10 raised to power 3. Just do the calculation. You will get the value of sigma St in Newton per mm square. Sorry, here you have to multiply it with length also. One small mistake. This is so sigma Cu, this is the strain multiplied by the length. Length is how much? Length is, this is 1.5 meter, so 1500. So this is 1500 and this will be 1000 and this should be equal to 0.03. Okay. So here I will change like this. So sigma Cu into 1500 minus sigma St divided by E of St into 1000. Okay, so here what I will do is, so sigma St into 1500 minus, this is sigma St divided by 200 into 10 raised to power 3 into 1000. This should be equal to 0.03. From here you can get the value of sigma St. Okay. Just do the calculation for this. Sigma St will be how much? So this will be 1.5. So I'll just modify this equation a bit. So this is 1.17117 is equal to 2 times of sigma st into 1.5. So this will be 3 times of sigma st divided by 100 plus sigma st divided by 200. So this will be 6 plus 1 7. So this is equal to 1.117 into 200 divided by 7. This will be your value of sigma st in Newton per mm square. So just do it. So this is how much? .117 into 200 divided by 7. So 31.91 sigma st is 31.91 Newton per mm square. This is the value of sigma st. Now using this sigma st, you can calculate the value of sigma cu. So sigma cu is equal to 2 times of, sigma st, one second, this is sigma st by 2. Again I made a mistake here. So this is, let's see this. So this is 1.117 minus sigma cu. So I will write it like this. This is sigma cu into 1500 divided by, this is 100 into 10 raised to power 3 Newton per mm square. Okay. Now this sigma st I will write down as 2 times of sigma cu divided by, this is 200 into 10 raised to power 3 into 1000. This is equal to 0.03. Now solving this, you can get the value of sigma cu. Okay, you can do the calculation, get the value of sigma cu, and from sigma cu you can get the value of sigma st, right? So how much it will be? So this is equal to 1.117 minus 0.03. This is equal to 2. So 1.2. 3 times of sigma cu plus 2 times of sigma cu divided by 200. So this will be 5. So this will be how much? This will be 1.117 minus 0.03 into 200 divided by 5. 43.48. Newton per mm square. This is the value of sigma cu, right? Now sigma st is twice of this value. So twice of this value will be 86.96 Newton per mm square. This is the value of sigma st and sigma cu, right? This is what is expected to you to calculate. Chalo, moving on with this, move to the next question. This is the question from shear force and bending moment diagram. Question says that a propped cantilever beam XY with an internal hinge at the middle is carrying a uniformly distributed load of 10 kilonewton per meter as shown in the figure. The vertical support reaction X in integer is. So you need to calculate this vertical support reaction at x. You need to calculate this vertical support reaction, this Vx you need to calculate, right? Now how to get the value of Vx? If we can calculate the value of Vy anyhow, if we can calculate the value of Vy, then taking the summation of vertical forces equal to 0, I can get the value of Vx. Okay, so let's name this point as C. This C is an internal hinge. It means that the total amount of moment acting on the portion Cy should be equal to 0. So I will write down summation of moment summation of moment on the portion Cy should be equal to 0. So due to this UDL, you have the clockwise moment. The value will be W into 2. So W is 10. 10 into 2 into 1. So this is the clockwise moment. Then you have the anti-clockwise moment due to this Vy, which will be Vy into 2. So minus Vy into 2. And this should be equal to 0. From here, the value of Vy will come out to be as 10 kilonewton. Okay. Now you know the value of Vy. What you can do is take the summation of vertical forces equal to 0. So when you take summation of vertical forces equal to 0, summation of vertical forces equal to 0, you have this 10 into 4 acting downwards. So 10 into 4 acting downwards, and this should be equal to Vx plus Vy. Vx plus Vy. So this is 40 equal to Vx I need to calculate. Vy I have already calculated as 10. So from here the value of Vx comes out to be as 30 kilonewton. This is my value of Vx. This is the value of Vx, right? So this is how we can solve this question. Chalo, moving on with this, next. So this is the question for which you need to calculate the axial force, shear force and the bending moment at a point Q for theta is equal to 45 degrees. This is the GATE previous year question, a very easy question. You can take this as an homework, right? Let's move on to this one. Question says that in the frame shown in the figure, not to the scale, all four members AB, BC, CD and AD have the same length and have same constant flexural rigidity. All the members A, B, C and D are rigid joints. The midpoints of A, B, C and D are denoted by E, F, G and H respectively. The frame is in an unstable equilibrium under the shown forces of magnitude P acting at E. Sorry, this is the stable equilibrium, not unstable. Acting at E and G, then which of the following statement is correct? Okay, so this is the frame shown to you. Then you need to identify which of the following statement is correct. Whether the shear force at H and F are 0, horizontal displacement at H and F are 0, vertical displacement at H and F are 0, or slopes of E, F, G, H and H are 0, right? So first of all, let me draw this frame in front of you. This is the frame shown to us. Okay, this is the frame shown to us and this is how the loading is done. This is one load P and this is another load P. Let me just name all the elements A, B, C, D, E, F, G, H. This is A, this is B, this is C and this is D. The midpoint is E, F, G and H. Okay, every time you need to analyze these kind of frames, better to go with the free body diagram. Okay, so let me draw the free body diagram for all the members. So one by one I just draw all the free body diagram for the members. This is my member AB. So this is my portion AB. For this portion AB, this is the load P acting at the midpoint, right? Midpoint is E. Due to this load, these two joints, which are the rigid joints, will going to provide the reaction moment. So this will going to sag the beam. So in order to have the reaction moment at MA and MB will act like this. Okay, and these reaction moments are provided by the joint. In order to keep this joint B in equilibrium, equal and opposite moment should act over this portion B, over this portion BC, right? Similarly, equal and opposite moment should act over this portion of A. Now, this is the load acting over this portion CD. This is C, this is D, right? Now, in order to keep this system in under equilibrium, if you are applying a load like this, these two rigid joints should apply the reaction moment like this. This is the reaction moment. This is how the reaction moment is applied. This is one reaction moment and this is another reaction moment. In order to keep this joint C in equilibrium, you have equal and opposite moment should act over this portion and equal and opposite moment should act over this portion. So this is the free body diagram for all the members ABCD. Now, if you observe this closely, these members will going to deflect like this. This is how they will going to deflect. This is how they will going to deflect. This is the deflected shape of these members I have drawn. Okay. Now, first of all, the first statement says that shear force at H and F are 0. Okay. This is H. This is H and this is F. You can clearly observe these two portions are under the action of pure bending. So whenever the members are under the action of pure bending, the net shear force over these two members will be 0. So member AD and BC, AD and BC are under pure bending. Hence, net shear force should be equal to 0. So this statement A is the correct statement. Now statement B, horizontal displacement and H and F are 0. You can clearly see this point H is moving vertically upwards and F is moving vertically downwards from this deflected shape. This is the new position of H. This is the new position of H and this is the new position of F. So H and F are moving vertically, they are not moving horizontally. So this statement is horizontal displacement of H and F are 0. So this statement is also correct. Now coming to the third statement, which says that the vertical displacement and H and F are 0. No, my dear. The vertical displacement and H and F are present. So this statement is totally incorrect. So this statement is incorrect. Statement C is incorrect. Statement D says that slopes of E, F, G and H are 0. Okay. You can see here, this point E, F, G and H are the points of maximum displacements. So wherever you will get maximum deflection, the slope has to be equal to 0. The slope has to be equal to 0. These are the points of 0 slope. So whenever you will have the maximum deflection, at that point you will have the 0 slope. So statement D is correct. So for this question, your statement A, B and D are the correct answers. Chalo, moving on with this. So this is the question from the bending stresses. You can just go for it. I'll give you 2 minutes of time. Just go for it. It's a very, very good question. Just go for it. Okay, so this is the question from bending stresses. Okay, so this is the question from bending stresses. Let's see this. The question says that the beam of cross section given below is subjected to a positive bending moment causing compression at the top of 16 kilonewton meter is acting around the horizontal axis. The tensile forces acting on the hashed area of the cross section is. Okay, so what you need to do? You need to find out the tensile forces which are acting in the hashed area. How can I say this, that tensile forces are acting on this portion? So first of all, calculate the depth of neutral axis. Since this is a rectangular cross section, so for rectangular cross section, the neutral axis will pass through the CG. And this is the CG. This is the CG, right? This is your neutral axis. That will pass 75 mm from the top fiber. The total depth is 150. So your neutral axis will pass from the 75 mm, right? Now this portion is under the action. This portion is under compression. This portion is under tension. We need to calculate the tensile force acting over this hashed area. So if I draw the shear stress, bending stress distribution for this, the bending stress distribution for this cross section will be like this. This is your bending stress distribution for this cross section, right? Now what you need to do is, you need to calculate the stress at this point. This stress I want. Say this value is some sigma 1. This is 0. So the tensile force over this hashed area, tensile force over hashed area is tensile force over this hashed area is equal to average stress, which is 0 plus sigma 1 divided by 2. This is the average stress multiplied by area of this hashed portion. So this is equal to 50 into 25. Okay. Now the question reduces to how to calculate the value of this sigma 1. So this sigma 1 can be calculated using bending equation. So bending equation is m upon I is equal to sigma upon y. Using this equation, I can get the value of sigma 1, right? For this, the value of y is 25 mm. M I already know, which is 16 kilonewton per meter. I can calculate. So I will write like this. M upon I is equal to sigma 1 divided by y1. So M is 16 kilonewton meter. So 16 into 10 is power 6. Divided by I, which is B. B is 50. This is how much? This is 100. B d cube divided by 12. So 100 into 150 cube divided by 12 is equal to sigma 1 divided by 25. From here you can calculate the value of sigma 1. Just do the calculation and tell me the answer. Just do the calculation for this and tell me the answer. What is the value of sigma 1? So the value of sigma 1 will be 14.22 Newton per mm square. The value of sigma 1 will be 14.22 Newton per mm square. Now you know the value of sigma 1, you can calculate the tensile force. So tensile force is equal to 0 plus sigma 1. Sigma 1 is 14.22. 0 plus 14.22 divided by 2 multiplied by area of the hatched portion, which is 50 into 25. So this is how we can do it. So this is how we can do it, right? So tensile force is 0 plus 14.22. So this comes out to be 8.89 kilonewton. This comes out to be 8.89 kilonewton, right? This is my final answer. Okay, so my dear students, with these questions, I will just like to end our today's session. Tomorrow we will going to continue with the other questions as well, right? We will going to see the other topics of shear stresses, torsion of shafts, principal stresses, and the most important topic of deflection. Then we have column analogy and thin pressure vessels. So all these topics we will going to cover in the tomorrow's session. For the regular updates regarding our YouTube schedules, you can join our Telegram group. And again, I am reminding you to get the lecture PDF. You will get this in our Telegram group, that is for our IMS GATE Academy. The link is given here itself and it is also provided in the description box. I will again like to remind you about the courses. We provide you with 800 hours of live teaching, whether it can be an online mode, offline mode, or the hybrid mode where you enjoy the fusion of online and offline teaching. Our offline centers are present in Bangalore and Vijayawada. You can contact our sir, which is our education counselor, naming Rahman sir, and he will going to guide you in the best possible way. If you want to feel like talking to the mentor, you can ask, you can call this number and you can speak to any one of us. So thank you so much for this session. Thank you so much for listening patiently. I hope this session would have been an effective one and will going to help you to revise the concepts of strength of material easily. I'll see you tomorrow, same time, same place, 12 p.m. at IMS GATE Academy YouTube platform. So that is all from my side today. Myself, Prateek Mishra, signing off with a smile. Thank you so much for being such a patient and lovely audience. Thank you so much.